there are advantages associated with Lagrangian mechanics. We're going to run through first the Newtonian method of solving this. Then we're going to run through the Lagrangian method, and that's going to illustrate those advantages I just talked about. It's going to throw straight into your face. So, first thing we want to do is we want to understand the problem we're dealing with. So, simple harmonic motion with a pendulum. Basically, we're going to have a pendulum going back and forth. We have a mass m, write that in, attached to a string that's going back and forth. We're assuming the string is not going to stretch. No friction at the connection point. I'm not going to have any air friction, so this is pretty easy. Now, Newtonian method. You guys have all seen this problem before, I hope. What do? First thing you do in the Newtonian method is you derive, or rather you draw out your free body diagram, put in your vectors and all of your forces, right? This is the thing we sidestep in Lagrangian mechanics. We don't have to do this in that. But in Newtonian mechanics, we have to invest some time in doing that. Fortunately for this problem, it's very simple, and the free body diagram is not convoluted. But when you take a look at complex systems, that can become very cumbersome. So it's nice when we avoid that, right? It's very nice when you avoid that. So what I'm going to do is I'm going to take our mass we have here, mass m, draw in our forces. So we have the force of gravity, it's always there, mg. And we're also going to have a tension force. These are all the forces that are acting on this guy. We know the angle between this vertical and that is theta. So from geometry, we know this also theta. It's law of geometry. And what I'm going to say is that we could take this and break it down in terms of x and y components. We could get a force like that. We're going to talk about that shortly. So, we've got a free body diagram. Now, what we want to do is we want to apply our laws of physics. Newton's second law. In this case, it's actually easier to consider torques, moments acting on this system. So that's what I'm going to use. We know from Newton's method, Newtonian mechanics, that sum of the torques has to be equal to I, the moment of inertia, times alpha, which is just the second derivative of theta, this guy here. Okay? So, we need to define our torques. We know torque is R cross F. Okay? So we needed to define our R coordinate. This is basically R, our R vector. So what we're going to do is, I'm going to say R is going to be defined as, well, in the x dimension, we have L sine theta. In the x dimension, the I hat. So basically, sine theta, it's going in this direction. For y, we have plus negative L cosine theta. Basically in this direction. We're just going straight down and treating this as our origin. And we do not have anything in the z direction. We're assuming this is planar. It's going to move in this plane. Okay? Forces, we have in the x dimension, we have negative t sine theta. In the y direction, we have t cosine theta. minus mg. And in the z direction, again, we have no forces. It's going to remain planar. So you see the Newtonian method is highly dependent upon our free body diagram, our vectors, figuring out our geometry. This is a simple problem. It's a very convoluted problem figuring out, your trig, your geometry, your vectors. It can become cumbersome very easily. The disadvantage of Newtonian mechanics, you see that. Big disadvantage. So, what we want to do is, we want to define this cross product. Okay. We're going to have an I, J, K. We're going to have R dimensions. So, we have L sine. We're going to have negative L cosine. That's 0. For F, we're going to have negative T sine theta. For the y component, we have T cosine theta minus mg, and then 0. And we're taking the cross product here. So, consider I. That times that is 0, minus 0 times that is 0. We consider j. 0 times that is 0. That times 0 is 0. Now, we consider k. We have L sine theta times T cosine theta minus mg minus those negative signs. Or let's back up a bit what I'm doing. I'm doing this times that minus that times that. So this becomes T L cosine theta sine theta, and it's still a vector, so we must put in k hat. Okay, so we see that we get TL sine theta cosine theta, bam, this cancels out with that guy, and we're left with negative MGL sine theta. That's nice. Very, very nice. So, this was sort of the long route I'm taking here because I want to understand the process you might have to go through with this. You have to take all your cross products, so on and so forth. We're dealing with vectors. That makes it convoluted. We can sidestep that with the Lagrangian method because it deals with scalars. Okay, that's an important thing to notice. It deals with scalars. So we just trust our mathematical intuition, work through the scalar quantities, and we get nice, simple results. Okay, that's a big advantage we get with the Lagrangian method. So what we could have done here, we could have figured out this component, and L times mg sine theta. That would give us the same result here. And again, it has to be negative because our thumb is going into the board, R cross F, right? So you could have done it like that, but that's the torque we're going to get, okay? So, we're going to make some board space and write down our result up in the corner. Don't forget that. Okay, so we figured out that T equals negative MGL sine theta. Okay? What's the next thing we have to do? The next thing we have to do is, we got to figure out the moments of inertia. It's a big component of Newtonian mechanics. Sometimes can take a lot of time depending on what you're dealing with. Fortunately, this is very easy. We have just a point mass attached to a string. So, we know that the definition of the moment inertia is r squared dm. Basically the distance to our mass. Okay? In this case, this is L. We have a mass And so this guy is L squared. And the integral just turns into a sum in essence. Basically the component, we move here, get that point mass, bam. So we just have ml squared, okay? I'll write that result here. Okay? And what we do is plug everything into our governing equation, okay? And that's how we get our result. So we end up with negative mgl sine theta, and that is equal to m L squared theta double dot. Now, if you're not familiar with those double dots, this guy right here, just to clear things up, if you have not seen that before, I know some people don't like doing that, this is equivalent to the following. Every time you see dots, you're dealing with this stuff, it's in terms of time, okay? So those dots are in terms of time. All right? So, this guy is our governing equation. This is our equation of motion. However, we can simplify it a bit. We can take bam, 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 bam. All right? So we end up with theta double dot is equal to negative g over L sine theta. Bam! This is the equation that governs our motion, okay? If you solve for theta, we would have theta sub t. We can determine theta at any time at all, and then we could figure out where this is located using the geometry. So in essence, this is the governing equation. This is what we were working for. This is what we wanted to get. Now, I could solve this. You guys have seen this, right? Hopefully this looks familiar, right? Root G over L is your frequency. Simple harmonic motion, baby. So, we get results with a cosine. Maybe I'll work through that after the Lagrangian method. But there's some kind of magic you have to do here. So I'm going to hold off a bit. So what do we find with using the Newtonian method? We saw we had to use a free body diagram. Not as nice. We had to use vectors. Not as nice. We had to draw them all in. Now we had to deal with our trigonometry, cosine, sines, cross products, the tedious work associated with vector quantities. And that's a disadvantage of Newtonian mechanics. It can take a while to get this result. Okay? And if your geometry is super complex, sometimes it's not even possible to solve Newtonian mechanics. It's super baffling, okay? That's where Lagrangian mechanics shines. And I'm going to show you a very hard problem that's almost impossible to solve in Newtonian mechanics. You try Lagrangian mechanics and bam, it's super easy. You get your solution super quickly, you trust your math, and it all makes sense. So what I want to do is I want to solve this using Lagrangian mechanics, okay? And I'm going to show you that we get the same result. So, first thing you want to do is figure out your geometry, your degrees of freedom, your coordinate system. We've already done that. We know that there is 1 degree of freedom because we only need one variable. We need to know information about one variable, which is the theta variable, to define where this object is at any time. Okay, because we know theta, we can figure out, L sine theta gives us x, negative L cosine theta gives us y. We can figure out where this is at any time if we know theta. That's 1 degree of freedom. What does that mean? What does that mean? I know you know it. I know you know it. Think about it for a second. That means that we have one Lagrange equation, okay? Because we have the same number of Lagrange equations as the degree of freedom. Okay? So, after we do that, what do we do? What do we do? Well, I'm just going to write that down. We just figured out our coordinate system. second here. All right, Lagrangian Mechanics. Our first example. You guys should be excited. I hope you are. Bam, Lagrangian Mechanics. First example, simple harmonic motion. Okay, so we got a coordinate system. We said that x is equal to L sine theta. I'm going to write y over here. It will become apparent in a second while I'm doing it like this. It's negative L cosine theta. Again, we're setting our origin right there at the top where it's connected. Okay, so what's the next step? The next step is we got to figure out how to get our Lagrangian. That's the master guy here. That's everything we work with. And we need to know the kinetic energy and the potential energy of the system. Now, T, which I'm going to call kinetic energy. Again, that's 1/2 mv squared. Well, we know that if we have a vector v, like that, we're going to have Vx and Vy, two components. And we know from the Pythagorean theorem, is actually the magnitude, it's not a vector, that the x squared plus y squared equals the hypotenuse squared. Right? So if we're trying to figure out this guy squared, the magnitude of that, this guy is just 1/2 m times x dot squared y dot squared. This is the same as the resultant velocity. All right? So in general, you always end up with this. Maybe you might have a z dot squared in there also to complete the Pythagorean theorem. So, what do we do? What do we do? In every problem, you're always going to define x and y in terms of your degree of freedom, or your degrees of freedom, and then you have to plug them in here somehow. How do we do that? How do we do that? Well, this is why I left space under here. You always have to compute x dot. So, let's do that. So, x dot becomes L cosine theta, theta dot. We got the chain rule in there. That guy pops out. And y dot. That's going to be L sine theta, theta dot. No. Derivative of cosine is negative sine. Negatives cancel. We're all good. So, we can plug these guys in here. And the kinetic energy ends up becoming x dot squared. We're going to have L theta dot cosine theta squared plus that guy, L theta dot sine theta quantity squared, baby. All right. And just a caveat, what's really cool about Lagrangian mechanics is as you start working through it, things pop out that make sense that you've seen in Physics 101. For example, this is omega cross r, right? We expect that. That's the tangential velocity, right? So, this is the x component and that's the y component of. So this makes sense. Now, what I'm going to do here is I'm going to write down the final results, explain what I'm doing. Okay. Squared theta dots. Squared. So what I did was I just used the fact that cosine squared theta sine squared theta is equal to 1. I took out the L squared theta dot squared, multiplied by this, that equals 1. Bam! We end up with our final result right there. All right. So, what we're going to do is we're going to take that, put it up here. important result is to make board space. All right, so let's get some space here. We'll leave our coordinate definitions because that's super, super important. And continue working. All right, what's the next thing we need to do? Well, we're trying to define the Lagrangian. So we got the T, we need the U, because the Lagrangian is the kinetic energy T minus the potential energy U. So we got to figure out what the potential energy is. Now this is the other tricky part of Lagrangian mechanics. I'm going to formalize this for you. What you need to understand is you're just using your Physics 101. That's all you're doing. Follow the principles, and they will lead you to the result you want. Trust in that. Trust yourself. You know what you're doing. You've learned this before. I used to have problems defining the potential energy, and I'll explain why. First, I want to say that for Physics 101, we know that the work is the negative integral of F dot dr. And that makes sense because if you think about work, you have to exert work to move this a distance r. I'm using a force to move that. So, the force times r, that's like the amount of effort, the work, the energy you have to exert to actually move this object. Okay? So, this is in here for conservative forces to work with the structure of physics. But what you need to understand is that if you apply this every time to your system, you're going to get everything right. What I had trouble with was the signs with U. It always made me uncomfortable. When I followed this, I could trust the math. I could trust my intuit. I could trust the physics, and that guided me to the results. So that's what I want you to do. Trust in this. Always apply this. So let's do it. Okay. What we know is that the only force in here, again, we ignore constraint forces. We're not going to consider the tension force because that's a fabricated force. Remember, one of the advantages associated with Lagrangian mechanics is we don't have to consider that. So the only force we have is the gravity force. And we moved this down below the origin and we moved it in favor with the force. So, in essence, if we call this the force of gravity, the distance we moved it was down. We let gravity exert itself on this. We let gravity do work. So if we think of it in terms of that, the system lost energy. It lost energy. If we had it here, we pulled it up. For example, if we had this up here at the origin, pulled it down here and let go and started our system, what we did was we took the potential energy it had at this point and we converted that into some kinetic energy to move it, and we lost that energy. It dissipated out of the system. Hence, you would think that the potential energy is negative because you lost some. You didn't gain some potential energy, you lost it. So when you move from here to here, that potential energy was lost. So we would expect U to be negative, okay? And when we follow this, that's going to happen. So the dot product between Fg and R, the dot product, F dot dr, I'll write it out. I won't be lazy. Just to help you guys, because I love you. This becomes just F, the magnitude of both vectors, times the cosine. Right? This cosine is 0. This becomes this guy and that guy. Bam. It's done. That's what it becomes. So we have an extra negative. We have to add that in. Okay? So what you're going to find is that if you have an origin and your particle is located below your origin all the time, your U is going to be negative because you exerted work to bring it down here. Basically, you let the force do its work. If you're above, and you're always above, it's going to end up being positive, right? Because you pulled it up, you put some potential energy in there, it has some energy to do extra work, right? You worked against the force of gravity. In that case, what you do is you get 180 for the angle between them, right? Let me draw this a bit better. You basically have R like this. You're working against the force. So this angle is 180 degrees. So hence you would get a negative. The negative would cancel out with that, and you would get a positive, right? So if we use this definition and do it as such, we end up with the following. What is our force? What is our force? What is our force? So our force is negative mg. What is the distance we traveled? Distance we traveled. The magnitude is L cosine theta. That is our U. Okay? That's our U. Very important quantity. Let's write that up here. All right? That's the U we get. So you see with Lagrangian mechanics, initially, the challenge is figuring out your potential energy and kinetic energy and doing it properly. However, and this is a big however, compared to Newtonian mechanics, we're only dealing with a first derivative. In Newtonian mechanics, your forces are equal to m times your acceleration. It's the second derivative. So that's one advantage. Another advantage I sort of glossed over, didn't include in the beginning of this video. Okay? So, what we're going to do is we're going to define next the Lagrangian. We have all the components we need. So, I guess I can get rid of this guy now. Don't need it anymore. So, Lagrangian, which is T minus U, is now 1/2 ml squared theta dot squared minus U. So minus minus becomes plus mg L cosine theta. Bam! This is the guy that's going to govern everything we do. You always want your Lagrangian when you're doing Lagrangian mechanics. Super, super important. Okay? So, again, we have 1 degree of freedom. What does that mean? It means we have 1 Lagrange's equation. So once we get this guy, we're going to work through the Lagrange equations for all our degrees of freedom. Hence, we're going to compute the following. Using the language of calculus of variations, using our understanding, we know that the first partial of the Lagrangian has to be with respect to the path variable. In this case, that's theta. We're trying to determine the path of theta. That's equal to the derivative with respect to the independent variable, that's time, of the partial of the Lagrangian with respect to theta dot. Okay? So, let's do that. Sometimes you may want to calculate these quantities individually. It's very complex. In this case, it's super easy, so I'm going to work straight off of that. So, theta. We're going to differentiate this in terms of theta. This does not have theta, that term. That does. We take the derivative of this. We end up with, the derivative of cosine is negative sine, so we end up with negative mg L sine theta. Ooh, that looks familiar, right? Next, we're going to have ddt, the derivative with respect to time, of this quantity. Now I want to differentiate in terms of the first derivative of theta. So this term doesn't have it. We ignore that guy. We differentiate this guy. So we have theta dot squared. That becomes 2 theta dot. This is ml squared theta dot. All right? And then we can take the derivative of this. Very easy. Theta dot becomes theta dot dot. Right? ml squared theta double dot. Looking familiar? So what I want to emphasize here. So that, as I talked about in my previous video, Lagrange's equations, this side ends up becoming a generalized force. I say generalized because it may not have the same dimensions, or rather units. Right? We won't have newtons, units for force. We actually have Newton meter. So it's a generalized force. That is always equal to the derivative of the generalized momentum. Right? And we got that because we ended up with ml squared theta dot. Well, what is this? This is just I omega, right? That's a momentum. And we always take the derivative of that. So, you know, Lagrangian mechanics is cool because once you work through all the math, you trust the math, bam, these quantities pop out that jive well with our intuition. That's super nice, right? It helps you feel comfortable. It helps you run through the derivation of what you're doing and say, I've seen that before. This makes sense. This makes sense. This looks like a torque. This looks like I omega. I've seen that before. I've done that in Newtonian Mechanics before. I'm doing it correctly. That's why I want to run through the Newtonian Mechanics portion first, so you see that, you know, we're going to get advantages over it, but at the same time, you know, we could use the information we did in Physics 101 that we learned in Physics 101 and other areas of physics to verify what we did, okay? But you can see here, we got the result very easily by just doing math. Very easily. We didn't have to draw out a free body diagram. We didn't have to consider the constraint force, this tension force, which can get very convoluted when we have a lot of normal forces, tension forces, especially when you're doing engineering mechanics. We didn't have to consider, you know, any geometry, any complicated trigonometry. All we did was, we got T, we got U, we plugged it into the Lagrangian, we got our Lagrange's equation. We got the result that we are familiar with. And I guess I could simplify this a bit further, just so it matches up what we saw previously. Make you guys feel comfortable. Bam. Cancel this guy, cancel that guy, cancel that, cancel that. Bring the L over here, so we get negative G over L. Sine theta is equal to theta dot dot. Now, once you get this, you can take your equation of motion, your governing equation, the equation that has all the information of how the system is going to evolve. Solve this baby. Bam, you got theta defined in terms of T. You can figure out where this particle, or this mass, is going to be located at any time. And hence, you got the solution you're looking for.